So welcome to the second lecture in this series of the Compton lecture series. So this is Tim Linden's lecture series, but I'm just giving a guest lecture this week while he's away traveling. He's actually in Japan at the moment for a conference, so that's kind of nice. So his topic is shining light on the dark side of the universe, and what he wanted me to talk about today with you is something very different to what he spoke about last week. So last week he covered some fundamental properties of light and how we can make observations using light. And this week I'm going to be talking about something very different altogether. I'm going to be talking about a huge component of our universe which doesn't interact with light, and it's called dark energy. And it's one of the leading mysteries in our understanding of cosmology and the universe today. So it really is a big question mark in our understanding of fundamental physics, and that's what makes it really exciting to study. So if you do have any questions, I would ask that you leave them until the end. There will be lots of time for questions, and it just kind of helps other people focus on the lecture a little bit more. Okay. But at the end, there are lots of time for questions. Okay, so the question for this lecture is, what is dark energy? And I can answer that straight away by telling you that we don't know. Okay, so I'm not going to be leading you up the garden path. There is not going to be an answer to this. This is cutting-edge research, bringing you right into the offices of what people are trying to understand today, what researchers, both observational and theorists in cosmology, are trying to understand. So this really is the billion-dollar question. So what is modern cosmology? In modern cosmology, what we're trying to understand is the evolution of the universe, how it came to be the way it is when we point our telescopes out into the night sky and we see lots and lots of beautiful galaxies at different redshifts at different times in the evolution of the universe. We're really trying to understand how it evolved from close to a time, close to t is equal to 0. Not exactly t is equal to 0, but close to that time. Describe the physics at this fraction of a second after the Big Bang through different epochs along its journey until today. And you can think about these different epochs as different chapters in the evolution of the universe, okay? Different stopping off points where we understand the physics very well. So for example, at about 380,000 years after the Big Bang, we have this so-called cosmic microwave background radiation, this first light. We're able to view the universe as it was at a very early time. We could also stop off at an epoch where the first stars are actually turning on. So before that, there's a dark age in the universe. There are no stars. And how does all that gas and dust condense and compress and really ignite into the first stars and shed light on the universe? So today's lecture really will not be stopping off on these epochs, but it'll be right up until today. What is happening at the current chapter in our universe? And that's not very boring at all. That's actually very exciting, because it's gone against our intuition of what we thought the universe was doing. We thought that it was a constant expansion, and really what we're finding out is that it's an accelerated expansion, that the expansion of the universe is speeding up. And we refer to this as the dark energy phenomenon. And then I'm also going to go from today beyond. I'm going to go a little bit into the future and start looking at, well, what will be the fate of our universe. So as I said, we can really think about this in terms of epochs of the universe, right? Chapters in the story of our universe, where we still don't know what the ending is going to be. And the theory of the Big Bang really is not the description of what happens at t is equal to 0, because we don't know what happened at t is equal to 0. The theory of the Big Bang is everything that happens after this time of the Planck time, which is a little bit before 10 to the minus 32 seconds, about 10 to the minus 48 seconds. And really, it's only from this point on that we really understand the physics very well, remarkably well, actually. And we can talk about things that happened after the Big Bang, like this period of rapid inflation of the universe, right? This rapid expansion, which we call inflation. We can then talk about a period where the whole universe was made up of just a dense soup of particles and light, referred to as this quark soup stage. Then we can talk about a stage where the particles start to combine and form heavier elements and the light gets released. We can talk about this stage here, moving forward only a second after the Big Bang. And then we can move forward and look at more familiar things like the formation of the first stars and then the first galaxies and then the modern universe. So really, this is a very long story, and I hope you understand that I can't cover it all in one lecture. But I'm going to be focusing on this last chapter here, the modern universe. So this chapter really is the dark energy era. And we believe that this chapter started about 5 billion years ago, based on our observations. So given an age of the universe of about 13.7 billion years, this is a relatively new phenomenon, right? And it came as a bit of a surprise to the community when we had these observations. So this is the era of an accelerated expansion. So I will go into more detail on the lead up to these observations and how it took the community by surprise. The next chapter I'm going to focus on towards the end of the talk is going forward beyond the modern universe. What is going to happen for our galaxy? So we know that the galaxy, our galaxy, the Milky Way, and Andromeda are actually on a collision course, and that in a few giga-years, a few billion years, they will merge and form an entirely new galaxy. Right? And what will the implications be for our solar system, for our sun? So we know, in fact, that our sun will get displaced to a new place in this new galaxy that will form, but we can do simulations and just make a guess on what is the likelihood that we'll end up maybe in a spiral arm or closer to the center of this new galaxy that will form. We know for certain that if this accelerated expansion continues at a constant rate, then all the galaxies are just going to redshift further and further away from us, and we're going to be sitting in a very lonely universe. We're not going to be able to see any of the other galaxies around us, and this is going to be a very sad time. We call this the cosmic blackout, which should happen in about 100 giga-years. But as I said, it all depends on the properties of dark energy, which we don't know. So what is going to happen, the fate of our universe, we still don't know. And this is why we need to know what is dark energy in order to answer this question conclusively. We do know that the stars will run out of their fuel in about 1,000 billion years, because their fuel is not infinite. So definitely we will have some sort of dark age coming upon the universe. So let's go right back to our understanding of cosmology, or the very beginnings of modern cosmology at the beginning of the 20th century. And what we had was, cosmology was a very early science. It was not the precision cosmology, the precision science that we talk about today. The notion of thinking outside of our solar system and outside of our galaxy was really very foreign. Whereas today, we routinely make measurements of other galaxies, distances to other galaxies at incredibly high redshifts and, a long time ago. But back in the early 1900s, this was, quite a bizarre idea to think about. And it really was a kind of fringe science. So the two people who kind of were leading this field at the moment were Einstein, pictured here, and William de Sitter. And Einstein wrote down his equations of general relativity, which he had worked on for nearly a decade. And his equations described the relationship between the mass, the matter you have in the universe, and the curvature of the universe, dynamics, how objects move in the universe. Okay? And at the time, there was a prevalence for the universe to be described as a static, unchanging place. This was quite a pleasing notion for people at the time. And so Einstein worked really hard to make the solutions to his equations give a static, unchanging universe. Okay? The heavens unchanged, in a sense. William de Sitter had a different solution to Einstein's equations of general relativity, which actually gave rise to an expanding universe. But it turned out that both of their solutions were not stable with matter in the equations. Right? The equations just did not work out. So ultimately, it was not for these theorists speculating to get to the right answer. It came from observations. And it was really in 1923 when Edwin Hubble made observations of distances to variable stars, which are called Cepheid variables. He was making these observations, and what he found was that the further away a galaxy is, the faster it's moving away from us. So in this picture here of the original data from 1929, we see measurements of the recession velocity in kilometers per second, given by the distance in this large astronomical unit of a megaparsec, which is a ginormous distance scale. You can see that there's this linear relationship between them. Okay, so the further away a galaxy is, the faster it's moving away from us. So this notion of no longer being a static universe, right? These objects which are further away from us are actually moving faster away from us. This gives rise to this notion of an expanding universe. And you can see here that the data points are pretty sparse and there's lots of scatter around this red line. So this was very early data hinting towards this phenomena. We now have exquisite measurements of this so-called Hubble diagram, which is measuring at different redshifts, so you can think about this as different distances in the universe, measuring this correlation, right, between the actual apparent magnitude of the object, the luminosity of the object, and its distance from us. So I'll talk a little bit more about what we use to make these observations, but this is really incredibly precise, and it's all pointing towards an expanding universe, but also today it's telling us that this expansion is accelerating. But in Hubble's time, this was very new. He was making measurements at very low redshift, right, very close distances to us. And this notion of an expanding universe was quite radical at the time. So if you think about this, the universe is expanding today. The galaxies which are further away from us are actually accelerating or moving faster away from us. This means that if we roll the clock backwards, right, a few billion years ago, everything was closer together. We keep rolling that clock backwards, and we have this analogy of the universe like an inflating balloon. So it's not a perfect analogy because obviously with an inflating balloon, you have a person here who's breathing air into the balloon. We don't have the same thing as the universe. We don't have a single point that the universe is inflating from. But this is just an analogy, as I said, and you can think about galaxies as being point masses or just little dots on the surface of a balloon, that when you inflate the balloon, the material of the balloon stretches, and that material is meant to represent the expansion of space-time. Yeah?
Galaxies that are somewhat closer are moving away at a slower rate than the farther ones. Would that be true?
Yes, that's right. They appear, so the ones that are further away appear dim. Yeah?
Within the galaxy, as the galaxies move away, but within the galaxy, does it stay the same?
Yes, that's right. So, yeah, so the analogy of these galaxies being points on the balloon is not perfect. You can think about those, a better analogy is imagine if you had ants on the surface of this balloon. As you inflated the balloon, the ants would be crawling around, but the ants themselves don't inflate. All right? And that's quite a good analogy because within a galaxy, the gravitational binding force of the galaxy is much stronger than the expansion of the universe. So within a galaxy, you don't actually feel the expansion of the universe. So we call galaxies gravitationally bound systems. They're not being disrupted or stretched by the expansion of space-time. It's the space in between the galaxies which is actually being stretched. So the cool thing with this is that you don't get these galaxies being stretched, as I said, but light particles, which are traveling through space-time, they actually lose energy, and we call this the red shifting of light. So light has a wavelength that's associated with it, and it loses energy as it travels through an expanding space-time. There's more of a distance to travel, and so it costs more energy for the light to travel through it. This property of light, this red shifting or lengthening of the wavelength of the light, is very important for cosmology because this is how we make our observations. Based on the wavelength of the light, we can actually tell how far our galaxies are from us. So understanding this red shifting of light or the stretching of the wavelength is really the essence of how we make measurements in cosmology. And this is what this cartoon movie is showing here. The yellow dots represent the galaxies, which don't change as we get an expansion of the universe. But the wavelength of the light, seen here as the little wiggles, they actually do change in color. So the wavelength of the light stretches as the universe expands with time. So as I said, when we take this notion of an expanding universe and we roll the clock backwards, we're brought back to this idea of a Big Bang, a point where everything is infinitely dense and hot. And as I said, the Big Bang theory, really, we don't know what happened at t is equal to 0, but it describes everything since t is equal to 0. So Einstein's equation of general relativity is just this, right? And it's remarkably beautiful and concise, but that's only if you understand what these indices and all these numbers mean. Yes?
What's inside the sphere and what's outside the surface of the sphere?
Yeah, so this analogy is basically not perfect. This is meant to represent all the physical matter or energy density in the universe, right? And with this sphere analogy, it's not perfect because we don't know what the curvature of our universe is. It's just meant to represent an expansion of space-time. So this balloon is not 100%, right? Maybe our universe is just a flat rubber sheet which is being stretched. Yeah?
Well, do we know what's inside? Or?
So everything we're talking about here is all the energy and matter and pressure, all those things count when you talk about the stuff in the universe. And one of the things Einstein's equation tells us is that it tells us about the connection between the expansion of the universe and the energy in the universe. So all that stuff of the balloon or of the rubber sheet that you're stretching, we're talking about all the materials in the universe. Okay, all the energy in the universe. And we also think about particles, matter, as being energy. So this is another one of Einstein's equations, E is equal to mc squared, where we're told that mass and energy are equivalent. So when we're doing a cosmic inventory, when we're counting up all the things in the universe, we consider energy and mass as being equivalent. One of the really beautiful things about general relativity is that if you can do that, if you can do a cosmic inventory and count up all the things in the universe, then you can figure out the expansion of the universe. That's what Einstein's equation tells you. This g mu nu here is the structure of space-time, how that rubber sheet is curved. Okay? And then this t mu nu, this is basically the stuff in the universe. And then everything out in front are just some constants that you don't need to worry about. But it's this equation, this left-hand side equals the right-hand side, tells us about some fundamental properties of our universe. Right? The curvature of the universe, how curved space-time is, and how it expands, depends on the stuff in the universe. And this is going to be important for dark energy, because dark energy is a new component of our universe. And it's causing something very profound to happen to the expansion of our universe. It's causing an acceleration in that expansion. Okay, so just to recap, this story of the expansion of the universe was what we believed to be the correct cosmological description right up until the early 1990s. We thought that the universe was expanding at a constant rate. So we had this notion of Hubbles Law, which related the velocities of objects given their distance to us. And you can see that this is a straight line. And we refer to this relationship here as a linear relationship with a constant between those two variables. And basically that gave us a constant expansion rate for our universe. That was the notion until the 1990s. And then it was in the early 1990s where some observations really started not to make a lot of sense within that picture. So you have this notion of a constant expansion of the universe. Einstein's equation tells us that if you sum up all the stuff in the universe, it should tell you how the universe is expanding or moving. So when people did this, people were counting the largest gravitationally bound objects we have in the universe, which are not galaxies, but actually groups of galaxies, clusters of galaxies. You can add up all these objects as a function of their mass, and then you can make this plot of how many objects you find as a function of mass. And then you can compare it with your theoretical predictions given Einstein's equations for what our expanding universe is doing and the amount of matter that should be in the universe. This is a theoretical prediction, this solid black line, whereas the observations were lying somewhere here. So what this observation was telling us in the early 1990s and 1992 was that the expansion of the universe was not equaling the amount of stuff in the universe. There was far less material stuff in the universe than the accelerated expansion, or the expansion was telling us. So the expanding universe was not the full story. We also had other observations. So what we can do is we can make theoretical predictions for what the age of the universe should be given the matter component that we measure in the universe, or that we think is in the universe. And people were coming up with a theoretical value for the age of the universe somewhere between 8 and 10 billion years. Okay? So we can make this measurement quite precisely given Einstein's equations, which tells us how the universe has been expanding given the stuff in it. Okay? But people making measurements, observations of the oldest globular clusters, these are clusters of old stars, came up with a very different number for the age of our universe. So this is quite an old measurement in the 1990s. We have much more precise measurements now, but they were coming up with something of about 15.2 billion years. So this is really very discrepant with this number from theory. So there really was something not adding up. But it was only in 1998 that there were two teams of astronomers who were looking at supernova stars. So supernova are basically stars which die. They are binary star systems that explode in a very, very massive, bright, brilliant explosion. And these two teams of astronomers were measuring these different catalogs of supernova And they both came to the same conclusion. They both found that supernovae were dimmer than expected from the predictions of general relativity and dark matter and luminous matter only. Okay? And these two teams actually won the Nobel Prize in Physics in 2011 for these observations which they made in 1998. So it was this observation of these two of these supernovae which really confirmed that we weren't looking at a constant expansion for our universe. We were looking at an accelerated expansion. So let me just talk you through briefly the idea of how we use supernova, or these dying stars, to make these observations. So to show you how bright these supernova are when they explode, this is a recent observation of a supernova. This is the Cigar galaxy called M82. This is a picture taken by the Hubble Space Telescope in 2013. And then early in 2014, you can see the same galaxy, and you can see a very big difference here, highlighted by the red arrow. So that is actually a Type 1a supernova going off in this galaxy. And the light from this explosion actually outshines the light from all the stars in the galaxy. Right? There are billions of stars in this galaxy, and this is the explosion of just one star. So there's a huge amount of light being produced in these explosions. So what are these? So the type of supernova that I'm going to be talking about, there are different types. The type that are important for cosmology are referred to as Type 1a, and they are binary star systems. So before this explosion happens, what's going on is that you have this white dwarf star, which is happily gobbling up or eating material from a companion star. Okay? But when this white dwarf star reaches a critical mass, you get an unstable situation happening within that star. It can no longer support itself. And what happens is it actually detonates in a massive nuclear reaction. It's a runaway reaction. And shown here in the top corner is actually a computer simulation of what's going on in these Type 1a supernova detonations. In this simulation, which we'll start again in a second, the detonation, or the runaway nuclear reaction, is happening close to the center of the star. It actually moves out towards the edge, and you can see what happens is a complete detonation of the entire star. So when the movie starts again, you'll see this happen, and you'll see that familiar mushroom cloud that we associate with nuclear bombs go off. So this really is, one of the largest nuclear bombs that we have, or we know about in nature. And this is why it produces so much light, and we're able to see these things outshine all the stars in the galaxy where they go off. So at the moment, there may be different types of progenitors. The type of star that is being accreted, that the white dwarf is accreting material from, may be different. But the actual detonation and the energy released in that detonation is very well understood. So this is why we call these exploding stars, we call them standard candles. This is because the actual amount of light, the amount of energy that is released when they detonate, is a fixed amount. And we understand that amount. It's like a bulb of a fixed wattage. Okay? We understand nuclear detonations quite well. And so we're able to understand the amount of energy released when these things go off. The fact that they're distributed at different distances from the Earth means that they act as standard candles. So we're able to say this is a light source of a fixed power, of a fixed wattage, but then it's distributed at different distances from us, and the light that reaches the Earth decreases as an inverse square law. We understand this quite well. So in this way, we're able to make distance measurements based on the light that reaches us. Right? Given the known source of the power of the source, we're able to determine the distance to these objects really well. And this is how they are standard candles in the universe. So those two teams of astronomers who were looking at these distant supernova stars actually found that they were dimmer than expected if you assumed the universe was a constant expansion rate. So this is this idea of an accelerated expansion. Not only were these distant galaxies moving away from us, they were moving away from us faster than we thought. So this is this notion of an accelerated expansion. And this is showing some data from those measurements. So the measurement of the supernova brightness here on the y-axis, and the supernova redshift, that's just a measure of their distance from us. And you can see that the data clearly prefer a model with dark energy, this unknown component which is causing an accelerated expansion, compared to a model with no dark energy here. Okay? And we actually have more and more observations which confirm these observations and this notion that we really need to include a dark energy in our theoretical models in order to explain these observations. So we no longer have a notion of a constant expansion of the universe. We have very good observations saying that the expansion has started to speed up or accelerate quite recently.
Question?
Yeah.
How do you account for those data points whose error bars are completely outside of the theory?
Yeah, so a lot goes into making these error bars here, okay? And based on, so you have a catalog of stars, and basically you make cuts based on different things like how well can you determine the redshift. So the error bars here, you can refer to some of these points as being outliers. So it's no one single point that you take when you're fitting for the model. It's the statistical distribution of all these points weighted by the error bars. So it's no one point which determines the cosmology. All of these things, when you compare observations with theory, they're done in a statistical sense. So it's the overwhelming number of points which prefer this model compared to this model. Right? It's no one point.
Just to clarify then, so that uppermost observation there,
Yeah.
so are we to say that that's moving so fast that it
No.
doesn't fit the statistic? I mean, it's moving faster
So each
than
of these
it should be?
observations has a lot of errors associated with it, right? And you have to quantify how well you understand your errors. And not all of these supernovae, not all of the redshift determination, not all of the measurements of those distances will be made perfectly, right? So some of these distances we've nailed, we know them really, really well, and some others we don't, right? So there's a varying discrete degree of understanding, and we're able to quantify that misunderstanding, right? So you do all these things in a statistical sense. So it is quite complicated. Yes?
Did you ask us to hold the questions to the end so that you could finish?
Yeah, I did.
I thought I heard you say that.
Yeah, I just didn't want to be ignoring people with their hands
You're
up.
very polite.
I'm sorry. I got
Okay,
it.
thank you for
What
reminding
you
me.
say.
Okay, so let's keep going. Okay, so the really intriguing thing is that we thought we understood what was going on, right? Einstein gave us the theory of general relativity, which actually does have a solution which predicts a expanding universe, right? Hubble's observation said, yeah, the universe is expanding, and we think it's expanding at a constant rate. We had lots of other measurements of all the stuff in the universe, right? All the matter and energy in the universe that we thought was there. And then we said, cool, okay, now we can fill this into Einstein's equation of general relativity and predict what's going to happen for the expansion of the universe. And then we have these supernova observations in 1998, which really contradicted this, right? And turned everything on its head. This does not fit in with general relativity and the amount of matter we know about in the universe, which are the dark matter and the luminous matter. So really, we need to add in a new component, which was not accounted for before, in order to explain these observations. And this really is the dark energy, the stuff we don't understand, but we know should be there. So this kind of brings you up to date with what is our modern cosmological model. So the way we express this is, if you want to represent all the stuff in the universe, we represented in terms of this pie chart. So the percentage of energy in the universe in different components. So unfortunately, the stuff that you're familiar with, like galaxies and you and me and luminous material, stuff that interacts with light, actually, depressingly, only represents 4.6% of all the stuff in the universe. You may or may not have heard about this other component, which is dark matter. Okay? So this is another matter component of the universe. We call it dark because it doesn't interact with light. But it represents about a quarter of our universe. I'm not going to be talking about this today, but Tim will be talking about this in a great detail during this lecture series, because that really is the focus of his research. So I'll leave that to him to talk about. But we have very good observations that suggest that this is a new form of matter. So you can think about this as another type of particle, like a proton or electron, but it just doesn't interact with light, but it interacts gravitationally. And this represents a huge component of our universe. But we really can't ignore this gigantic slice of the pie over here, which is this dark energy. And this is the stuff that I'm interested in and that I work on. And this is even more depressing because this represents nearly 3/4 of our universe, and we don't know what it is. So this brings us to our modern cosmology model of cosmology, which we refer to as lambda CDM. Okay. The lambda here represents this dark energy component, and we don't know what that is. And the CDM represents cold dark matter, and we don't know what that is either. So you could say, well, we can't really be very proud of this model, but we actually are incredibly proud of this model because even though we don't know what these two components are in detail, given how they interact with the rest of the stuff in the universe, this model has been incredibly, incredibly successful in describing a host of observations. So even though we don't know in detail what the dark matter particle is, we don't know exactly what its mass is, we don't know, well, does it interact with some other elements or some other atoms here in this visible component? We don't know some of those detailed questions yet. But given just its gravitational interaction, we're able to fit a host of observations. And the same with the notion of dark energy. So with dark energy, we're fairly certain. So the reason I have a picture of Mike Turner here, who is a professor at the University of Chicago, is that he actually gave dark energy its name. The alternative I think he was thinking of for it was strange energy, so I don't like that too much, so I much prefer dark energy. So you can really, we're pretty certain that dark energy is not a new particle, okay? That it really is made up of energy, and you can think about it as an energy field in the universe. I'll talk more about that in a few slides. So dark energy is actually incredibly important, even though it's a recent phenomenon. I said the effects of dark energy have just started to have an impact on the growth of structure in our universe quite recently, about 5 billion years ago. It's very important because the matter in our universe interacts gravitationally and it wants to collapse. Okay, structure wants to form. Galaxies collapse, and then we get galaxies also being gravitationally bound to one another in clusters of galaxies. And then if it wasn't for dark energy, we would get clusters of galaxies clustering with other clusters of galaxies, and we would get so-called superclusters. And matter would just continue to grow up gravitationally. Dark energy has stopped that happening. Dark energy is this recent accelerated expansion of the universe. So what this means is that dark energy is actually acting like a repulsive gravitational force on very large scales. So even though the universe wanted maybe to form superclusters, clusters of galaxies, it no longer is able to do that because of the properties of dark energy. Dark energy is actually acting like a repulsive force on very large scales. So when we're trying to understand these different chapters in the evolution of our universe, these different epochs, we have to understand this cosmic tug of war that is going on now between dark matter, which wants to collapse and form bigger and bigger structures, and the properties of this dark energy, which are actually causing objects to move further away from one another faster. So how do we explain these observations? I mean, we thought we had a really nice theory, general relativity, which is really beautiful and explains so many observations. And then we had that pie chart where before we knew about dark energy, there was just the luminous component and the dark matter component. So now we can try to understand these observations of the accelerated expansion by maybe speculating, well, what if dark energy is a new component in the universe? Not exactly a new particle, but what if it's a new field? So the analogy with this is the recently discovered Higgs boson, which is a scalar field. It's responsible for giving particles in our universe their mass. So what if dark energy was a similar type of field, which had energy density associated with it at every point in space and time? So if we think about this, and we're now thinking at the level of particles, right? We're no longer thinking about really large cosmological scales. Now we have to start thinking about quantum mechanics and quantum field theory. So when you try to think about the physics of quantum field theory and quantum mechanics, one of the things that is for certain is that our intuition is invariably wrong. This is the kind of crazy, wacky world where virtual particles can pop into existence and then disappear. So it's very hard with a classical mindset to understand quantum mechanics. Even Einstein himself had a real problem with quantum mechanics and refused to accept it. But we now know that it is the correct description of physics at very, very small scales, at the level of particles. So what does this mean for dark energy? If we're saying that maybe dark energy is a new field, which is everywhere in space and time and has an energy density associated with it, what does quantum field theory or quantum mechanics tell us about that? Well, one of the really cool things about quantum mechanics is that our classical notion of empty space or a vacuum as something where nothing is there, there is no energy, it's just empty. That is no longer true in a quantum world. In a quantum world, the vacuum is actually a very busy place. And the vacuum is a place where virtual particles, these particles which pop into existence and then disappear again, these things can routinely happen. And when particles pop into existence, we know that there's an energy associated with them. And maybe this energy associated with those virtual particles can represent a field, an energy field, which could be the dark energy. And the really cool thing is that the properties of this quantum vacuum are exactly the properties of dark energy. They represent a negative or repulsive force in the universe. So that is very enticing. And a lot of people believe that the answer to what dark energy is actually the vacuum energy, the energy associated with the vacuum. So the notion of these virtual particles, particle pairs, a particle and its antiparticle or antimatter, popping into existence and disappearing, this is not science fiction, right? This is science fact. We know that this does happen. Every particle that we know about has a non-zero probability in quantum mechanics to appear with its particle and antiparticle in a vacuum situation. Okay, and we've actually measured this with virtual photons, virtual light particles in the lab. So this is known as the Casimir effect, and it has been measured. And this actually generates, due to the geometry of this experiment, it generates a repulsive force between these smooth parallel plates. So this is an example of virtual particles associated with the photon, and the geometry of this experiment actually causing a repulsive force. So these virtual particles do exist. This nice simulation here is by Derek Lineweber, and this is actually a computer simulation using the equations of quantum chromodynamics. So this is another area of quantum field theory. And basically this is showing the energy density associated with the virtual particles that appear within this theory. So this is really nice, okay? We have this notion of, on very small scales, there's a non-zero probability for these virtual particles to pop up and cause a non-negative energy density in the universe. And they also correspond to a repulsive pressure in the universe. So this notion is great. I mean, maybe dark energy just is this constant energy density, which we call the cosmological constant, and we don't need to worry about dark energy anymore. We can all just go home, right? The theory is solved. But we actually need to do the calculation, right? So when we take our cosmological observations of what the energy density of dark energy should be, we get this very, very small but non-zero value of 10 to the minus 30 grams in a centimeter cubed. Right? That is a tiny, tiny value. That's a very, very low but non-zero energy density of the dark energy. Right? And the fact that it's non-zero is really incredible, but the fact that it's very close to zero is very disturbing as well. Then we go to our quantum field theory and we say, okay, well, we know that these virtual particles should be popping up, and we know that this should happen for all the particles that we know about in the universe. And we do our calculation adding up all the energy density that should be associated with the quantum vacuum. And we reach this value of 10 to the 74 grams per centimeter cubed. Okay? So this is a ginormous number. Right? This is a difference of 1 with 120 zeros after it. Right? This is by no means a small difference in your calculation. You can't just brush this difference under the rug. This is what you measure from the real universe, and this is what your mathematics is telling you. Right? So clearly the mathematics is wrong. So we can't just walk away from this and say, it's the properties of the vacuum. It's the virtual particles or the cosmological constant which are causing the accelerated expansion. So what is the other thing we can think about? So when I had the slide up saying how do we explain these observations, we have general relativity, and maybe we can think about a new component, a new energy density in our universe. Well, the other thing we could also do is, well, maybe general relativity needs to be revisited on certain scales. Maybe our theory of gravity itself needs to be modified. And on very large scales, if we modify our theory of gravity, we can then explain this repulsive force, or repulsive dark energy, which is causing an accelerated expansion. And this would make sense because on galactic scales, gravity is the most important force. On very, very small scales, we know that quantum mechanics describes the other fundamental forces of nature, right? We have the strong force, which keeps things like protons and neutrons together within atoms, right? We also have the weak force, which is associated with other types of particles. We have the electromagnetic force, which is associated with the properties of light. But on very large scales, the dominant force in our universe is gravity. So if we're trying to explain these observations on really large scales of acceleration of these galaxies away from one another, then maybe the force we need to be modifying is gravity. So that might seem a bit crazy because, Einstein wrote down these equations, and why would you tinker around with something that Einstein wrote down? We should really just believe it. But it's not so crazy to think about changing our theory of gravity. We're not throwing general relativity in the bin. We're just saying on some scales it needs to be modified. And we can really think about some lessons from history. Before we had the theory of general relativity, we had observations that we couldn't explain. So what we had were observations of the precession of Mercury around the Sun as it orbited around the Sun. And at the time, our understanding of gravity was just according to Newton. Okay? Newton told us about the relationship or the gravitational force between objects being proportional to the inverse of the distance between those objects, and also being proportional to the mass of the two objects. A very simple description for the gravity. But there were some anomalous observations in the motion of Mercury which we could not explain using Newtonian gravity. So at the time, there were early on, a French astronomer called Leverrier actually hypothesized, well, what if there's a new planet? What if there's new stuff in the universe which is causing a new gravitational force and causing Mercury to orbit a little bit differently than Newtonian gravity would suggest? And he actually hypothesized the presence of a new planet in between Mercury and the Sun, and he called this new planet Vulcan. People went off looking for this new planet, and of course they didn't find it because there wasn't a new planet. So this is one example of where we had observations we couldn't explain, and we thought, well, what if our understanding of gravity according to Newton is correct, but there's new stuff in the universe? So we went off looking for that new stuff, and we didn't find it. Einstein then came along and said, well, what now if we change our theory of gravity, our understanding of gravity? Einstein's description of gravity is still correct close to the Earth and in small gravitational regimes, so when you're talking about the mass of objects being very small. But on the scales of solar systems, you really need to think about general relativity. We need to think about gravity in a different way. We need to think about curvature of space-time. So you can think about this deformation of a rubber sheet. You can think about bowling balls sitting on this rubber sheet, deforming the rubber sheet. And now, if you were to move objects around this rubber sheet, which is being deformed, then those objects would move differently if those bowling balls weren't there. So you can think about this the same way as the Sun as being that massive bowling ball, and then the planets as being small marbles which are rolling around on the rubber sheet around the bowling ball. Okay, so the deformation of that rubber sheet is the curvature of space-time, and Einstein's description of relativity tells us that if you have a curvature of space-time, how objects will move in that space-time. So it turned out that in order to explain these anomalous observations, that we had to modify general relativity in order to get the right answer. So if we're trying to explain dark energy, my point is that maybe it's not so crazy to think about changing our theory of gravity. The only problem is if you're a theorist working in modern cosmology, it's incredibly difficult to change general relativity and still explain all the observations. The theory of Newton and Einstein is incredibly accurate at explaining all observations, and they have been annoyingly successful at explaining a host of observations. So, for example, if we just look within our own solar system, tests of general relativity, well, as I mentioned, we now have really superb measurements of this precession of the perihelion shift of Mercury, which are, agreeing with the predictions of general relativity to 0.3%. So these are very accurate measurements of the motion of astronomical objects, which are agreeing with general relativity. We also have measurements from the Cassini spacecraft, which went out into our solar system to study Saturn. And on its way, it actually sent signals back past our sun to the Earth. And the actual deflection of those signals in the warped space-time, as I was talking about before, this would cause a delay in the signal from the spacecraft to Earth. We can actually make a calculation using general relativity for what this delay should be, and it agreed with the measurements from the Cassini spacecraft to 0.002%. Right? So really, on the scale of our solar system, general relativity is really the end of the story. Right? These are incredibly accurate measurements in our solar system. So we know that on those scales, we can't tinker around with general relativity too much. What about when we go out, into other places in the universe? Well, we also have observations of much larger objects. So, for example, binary pulsars. These are rotating neutron stars, a binary pair rotating around one another. And these two are very massive. They actually act as light beams in the universe, emitting pulses at very constant frequency. But these two binary pulsars are actually gravitationally interacting and losing energy due to their motion around one another. And the actual measurements of the energy lost from these binary pulsar orbits agrees to about 0.2% with the predictions of general relativity. So there are certain places in the universe where our theoretical predictions for general relativity are in exquisite agreement with our observations. So if we're going to modify our theory of gravity, we really need to make sure that we don't mess up the success of general relativity, but in other places in the universe where we're trying to give an accelerated expansion, we do modify our theory of gravity on those really large scales, and we cause the effects of gravity to be a repulsive force rather than an attractive force. But just to give you an example of how tough it is to modify gravity in so much observations on all scales, these are the type of equations that you need to be looking at every day if you're going to modify gravity. So I hope you remember before from a few slides I wrote down that one simple equation which was general relativity, and this is how murky and mucky things get if you try to modify gravity and still be consistent with observations. So what then is the incentive for doing this? Okay? The incentive is we know that general relativity is not the full story. We know that general relativity breaks down in certain regimes and does not describe the physics in very high density regimes. So we know that we have singularities. So for example, black holes. General relativity and our description of gravity close to black holes is not exact. And we're not able to describe what is going on at the center of singularities. So this is the motivation for trying to modify gravity in order to explain those observations. So really tackling the question of what is dark energy is a very complicated thing if you try to either add a new component to the universe or modify your theory of gravity. And this is why it really is cutting-edge science, and it is something that is very intriguing and interesting to study. Okay, so I'm going to move forward now and speculate wildly about what the destiny of our universe is going to be. And this is the kind of fun stuff because we don't know what the answer is to what is dark energy, but we do know for certain that knowing what dark energy is will determine the fate of our universe. So before we knew what dark energy was, people thought that it was the geometry of the universe which determined our fate. Okay? It was whether our universe was flat, or maybe what we call a closed universe, or an open universe shaped like a sphere, or maybe shaped like a saddle. And it was the components, the stuff in the universe, which determined the curvature, the shape of the universe, according to general relativity. That would determine the fate of our universe, whether we would keep expanding forever, whether the universe would recollapse in on itself like another Big Bang or an anti-Big Bang, or whether we would actually speed up in our acceleration. But with this advent of the dark energy era, this epoch of dark energy, this new unknown component, we know what it's doing right now. We know that it's causing an accelerated expansion, but we don't know what it's going to be doing in a billion years from now. So we cannot really tell you what the destiny of our universe is going to be. But we know that the ultimate fate of our universe depends on the properties of dark energy. And we represent those properties, right, these fundamental things like the pressure and the energy density of dark energy. We represent it as this one constant here, W. We call this the equation of state of dark energy. So it's literally the relationship between the pressure of dark energy and its energy density. And depending on the value of W really will determine the ultimate fate for our universe. Okay, so let me walk you through the possible scenarios depending on what dark energy is. So we have this notion of starting off at a Big Bang and then having an accelerated expansion to our universe today. If dark energy is a constant energy density, right? So if it is that energy of the vacuum, which is just a constant with time and will always stay constant, then this acceleration will just continue. Galaxies which are accelerating away from us will just continue accelerating away from us. The light from them will redshift, right? It'll move to such a low frequency that we won't be able to observe them anymore. And ultimately, it will be a very lonely environment for us. Our galaxy is still gravitationally bound, or when we merge with the Andromeda galaxy, we will be a gravitationally bound galaxy, but it will just be very lonely as we look out into the universe. And we call this the cosmic blackout, which, given this constant acceleration, should happen in about 100 billion years. We know the stars will run out of their fuel. So things will start to turn very dark then. Not only will we be on our own, but even stars within our own galaxies will burn out. And that will happen in about 1 trillion years, 1,000 billion years. We also have evidence of the Big Bang. I refer to this cosmic microwave background radiation. Tim also spoke about it last week. So this leftover radiation from the Big Bang. When it was first produced at about 380,000 years after the Big Bang, it was at a very high temperature. It was a temperature of about 3,000 Kelvin. And when it was produced in the visible wavelength. So the light at that time, we would have been able to see with our eyes. You wouldn't have wanted to look at it directly because it would have blinded you, but it was in the visible wavelength. That light of that cosmic background radiation has since cooled and redshifted on its way to us. It has cooled to a temperature of about 3 Kelvin, and it is redshifted into the microwave wavelength range. And this is why we call it the cosmic microwave background. In the future, that radiation will redshift again and lose temperature even more. And it'll redshift to such low frequencies that we will not have any evidence, and we will not be able to make any measurements of the cosmic microwave background. So if you like, we are living in a very special time where we're able to make these measurements of observations of the Big Bang. So that is one scenario for the destiny of our universe. Another scenario is, well, what if this equation of state, this relationship between the pressure and the energy density of this unknown dark energy, what if this changes? And if this changes, the acceleration can actually ramp up, right? And if this happens, the repulsive force of gravity associated with dark energy can actually start to affect galaxies themselves. So this goes back to your question earlier of, inside galaxies, are we being affected by the accelerated expansion? So currently, no, but if dark energy ramps up in its repulsive force, it will start to rip clusters of galaxies and galaxies apart. And in that scenario, we call this the Big Rip scenario, all large-scale structure will actually be disrupted and torn apart. The other scenario is, well, what if we're just in a fleeting stage of accelerating expansion? Right? What if things calm down and we go back to just being a constant expansion rate? Things could actually turn around and we could actually go to being a decelerating expansion due to the gravity in our universe. Maybe the repulsive gravity associated with dark energy is actually overcome by the normal attractive force of gravity that we associate with normal matter. And in this scenario, the acceleration can become a deceleration, and we could actually be looking at a future where the universe recollapses into what people are calling a big crunch scenario. So there are some theories where we go into a big crunch scenario, and this arrow moves forward and actually joins up with a big bang, where you actually start accelerating into a new type of universe. So these theories are called cyclic universes, because this just keeps taking place over and over again. And these are, a lot of people work on these theories, and they are very interesting to work on. And one of the kind of cool things people are looking at are, if our universe has come from a previous universe, would there be any observational signatures or any ripples from this big crunch which may make it through the singularity and imprint on large-scale structure today? So these things are very fun and interesting to think about, but they are really the big questions of what's going to happen to our universe. And there's some serious mathematics behind trying to describe this big crunch and big bang scenario. Okay. So this lecture was, the title of this lecture was, What is Dark Energy? And as I said in the beginning, we don't know what that is. But I hope I've taken you through what current cosmologists are thinking, what might be the answers, and what are our justifications for looking for maybe a new form of energy or modifying gravity in order to answer these questions. And if we want to know what is the ultimate fate of our universe, then we need to know what the properties of this new component are, dark energy. And really going after this dark energy equation of state, this is what many, many missions, so ongoing missions like the South Pole Telescope and the Dark Energy Survey, these are the questions that these surveys are going after. And in the next 10 years, we're going to have lots more surveys going up from NASA and also the European Space Agency, both ground and space-based satellites, which are going after this question of what is the dark energy. Right? So this really is a million-dollar question, and a lot of time and energy is being invested in the next decade to answer this question. So I'll leave it there, and thank you very much for your time. And if you have any questions, please ask me.
I just wanted to ask about this correlation between the matter, the regular matter that exists. If I understand it, you're saying that virtual particles come from the 4.5% matter that is producing this quantum jitter, like virtual particles. So if the assumption is that that becomes a field, and that becomes the energy field, how will that field be affected if there's less of the regular matter? Can the virtual particles, if they only come from the existing matter, if the matter lessens, will that change the whole field?
So when we do that calculation of the energy associated with virtual particles, given all the particles we know about in the universe, that's how we reach that astronomical figure of 10 to the 74 grams. Where we're adding up, we know all these particles exist in the universe. We know that there should be an energy density associated with the vacuum given these particles. Right? And you may say, well, what if we're counting too many particles? What if there only should be virtual particles associated with a few of the particles we know about? And that's a great question, if that's what you're asking. The problem still exists, and it's still orders of magnitude greater than the amount we measure for dark energy. If we only took into account, for example, an electron and a proton, right, and we calculated the energy associated with virtual particle pairs, we still would be orders of magnitude way, way off in our calculation compared to what the dark energy density is measured to be. So this really is a huge, huge problem. Yeah, but that's a very good question. Any other questions? Yeah?
Directly about it, so is that another way of saying that dark energy is not like, you're like, well, what is this energy really coming from? It's like, why is there not enough of it?
So when we do our theoretical calculation, we end up with way too much energy associated with the vacuum.
So the trick is like, why is it?
So the puzzle is we measure a very, very small energy density in the universe, right? Very close to 0, 10 to the minus 30, right? It's a tiny, tiny number. Why is that so small when we sum up all the energies that's associated with the particles which we know about, right? And we know quantum field theory works really well. Right? So this should be right. Our calculation on pen and paper should be right. We get a huge number for the energy density. So this discrepancy, why is it so big when the measured value is so small? That's the real puzzle. And what people think,
So they were expecting to find this energy, but they were expecting to find it much bigger, right, originally? Or?
Well, it was more a case of the measured value was small, and then the theoretical value was expected to match or be close to the small value as well. The theoretical value ends up being ginormous.
That's it.
Yeah, yeah. So it was more that the observations came first, and then the theory was worked out second. So what people think is going on, if you believe that it's a cosmological constant, and a lot of people do, what people think is that we're actually missing some kind of symmetry. Right? So we have these symmetries associated with quantum field theory, and if we're missing a symmetry, then this symmetry could cause this vacuum energy, the energy associated with the vacuum, to be cancelled in a sense, and to be very close to 0, but not. So a lot of people think it's our theoretical understanding which is missing, which may explain that discrepancy. Yeah.
So I once heard a cosmologist speaking of general relativity say, I think I can quote more or less verbatim, that the Big Bang did not occur in a pre-existing space, time even, which to me is another way of saying that there was a period of, or a point of infinitely small volume, which is essentially 0. And another way of saying that there was a t equals 0. And so with that understanding, this quantum field theory, quantum field from which the virtual particles might be thought to arise, how can you consistently speak of a field that has 0 dimension? And also with time, if you don't know what happened before a certain time, 10 to the minus, how can you consistently speak of 1 second after t equals 0?
So
Like
the
you
theory,
don't know what was
the theory
before
of the
that.
Big Bang is not, we do not talk before the Planck time, t is equal to minus 48 seconds. Okay?
But how do you
That's
even
the
know
standard.
there was a t equals 0?
So we have precise, very precise measurements of our descriptions, our mathematical equations describe very well what is happening up to that time in terms of the fundamental interactions of the particles and the quark soup that is happening at that time and the subsequent evolution. Okay? So you cannot understand these things in terms of a classical mindset because the actual equations that go into describing these things, your classical notions break down. Okay? And I know that's very unsatisfying for me to tell you that, but that's just the way it is, right? When you talk about going back to very, very high densities and early times in the universe, classical physics from high school or even undergraduate physics at university are not enough to describe what's going on there. You're talking about a regime of very complicated mathematics and symmetries that are going on at those early times. Okay? In our current Big Bang model, we do not talk about t is equal to 0. In these models of the cyclic universe, where you are talking about going inside that singularity, trying to make sure that the mathematics is well behaved. So what I mean by well behaved is that you don't end up with infinities, you don't end up with things blowing up as you get to this point of infinite density and temperature and so on. Those things are controlled by the mathematics involved, and those things you cannot understand classically. Okay? It's very complicated mathematics going on there, right? And you end up with notions of the space-time and following what's going on with the space-time.
In the cyclical description with the big crunch, would you speak of a prior universe as a term you did?
So in the cyclical universe,
would that
people
be
who
a
work
t minus something?
people who work on the cyclical universe, exactly. There is a previous universe, and the notion of time is eternal. So when you ascribe a t is equal to 0 is completely subjective.
Arbitrary.
It's not arbitrary. Once you call a time t is equal to 0, then it's well specified, but it is subjective. So these are incredibly complicated theories. People still argue about the mathematics of trying to get through this Big Bang and into a big crunch scenario. But let me just say that trying to understand these things with classical physics is really impossible. You cannot do it. I'm just sorry that you can't do that, but you can't. Okay? That's just the way it is. The mathematics gets really complicated, and if you want to understand what's going on, then you need to study general relativity and quantum gravity. Yes?
Which part of this puzzle do you work on?
So I work on the modification to the gravity side. I actually work on both sides of understanding what dark energy is. So my research is based around these observations of large-scale structure. So I'm interested in how galaxies are forming on really large scales, and actually the positions of galaxies, how they're grouping together under gravity. And if we understand how this is happening, right, and we're trying to explain this accelerated expansion, I tinker around with equations and say, well, what if I modify gravity in this way, and in this way, and in this way? How does this change the distribution of galaxies, and how does it also fit in with our observations? That's one element that I work on, and that's kind of fun and cool to do, because as I mentioned before, it's difficult to modify gravity and explain all the observations, but you can do it. The other cool thing to do is to think about, well, what if there's a new component, this new energy field in our universe, and if this is changing over time, how can it impact galaxies and how they're distributed in the universe, things like this. So these things can be answered using computer simulations, and these are really fun to play around with. But ultimately then comparing with the observations and producing predictions for what future surveys should see as well. Yeah?
This acceleration started taking effect about 5 billion years ago?
Yes.
Or was it new? Maybe that was when the regular matter expanded to a point where gravity became not strong enough to hold us together, and this virtual or this dark energy maybe a constant, but it started being stronger than gravity at that point of expansion.
Yeah, that's a good question. Yeah, that's a good point. So the reason why we're seeing dark energy today is not just that it suddenly appeared in our universe. It's that it was always there, but because it's a very low energy density and our universe is expanding, at different epochs in our universe was being dominated, or the energy budget of our universe was being dominated by different components at different epochs. So as we talk about the very early universe, it was actually radiation, the energy associated with photons, that was dominating the behavior or the expansion of the universe. We then moved into a different epoch, which was the matter domination epoch, right, where the energy density associated with matter dominated. And as the universe expands, you get a diluting of the effect of dark matter. And actually, this is why we're in an epoch now where the dark energy is dominating the expansion. So that's a really, really good point. The real puzzle is, why are we just at an epoch where we can make this observation? Right? If we were living 5 billion years ago, we wouldn't have known anything about dark energy. If we are living maybe 10 million years into the future, all the galaxies would have redshifted away from us, and we would have just thought we were the only galaxy in a very lonely and empty universe. So one of those questions that's a real puzzle is, why is this just happening today, and why are we living in a special time in the universe where we can make these observations?
Our solar system has been around 5 billion years.
Yeah, I'm going to take a question from someone new just for a second. Yeah.
What can you say about the law of conservation of energy on a cosmological scale?
Yeah. So the conservation of energy that we associate with a classical notion gets modified when you talk about space-time. Okay? So it's actually a notion of a stress energy, which is conserved. You still have a conservation of energy, but it gets modified. So the analogy for this is that you can think about time as being simultaneous in a classical sense. Right? We think about two things happening at the same time in the world. Right? When I look at my watch and someone on the International Space Station looks at their watch, classically, a person with classical thinking says those two things happen at the same time. Okay? But we know, because Einstein wrote down the theory of special relativity, we know that that's not true. The time is not simultaneous. And that when you are moving, the actual speed of time slows down. So the classical notions of fundamental concepts like space and time have to be modified when you move out into the universe. Okay, so thinking classically can be very dangerous. Good question. Yes, in fact?
I guess Einstein didn't know about the accelerating expansion of the universe. Did he have any inkling, or would he have had to think of modifying his own theory?
So he didn't have any inkling, no. So he had this prejudice at the time, which was just a common thought in the community, which was the universe had to be static. Solutions to his equations suggested an expanding universe, not an accelerating expansion, but an expanding universe. In order to counteract that expansion, Einstein added in a term to his equations. Okay, to counteract the expansion, he added in another term, which would cause everything to be static. Okay, so kind of a repulsive expansion term in order to counteract the expansion. Then, after Hubble's observations, he removed that term and admitted, the universe is expanding, and I should have trusted my equations all along. It turns out that the term that he added in, that repulsive energy term, is similar to the terms that we add in now to explain this accelerated expansion. But that was just a coincidence in terms of a mathematical term that you would write in the equation to give a certain effect. Okay? It wasn't that Einstein predicted the dark energy or the accelerated expansion, because he had no notion of that happening. Yeah?
Is it possible that some sort of modified theory of general relativity that addressed the effects of gravity between galaxies could explain this whole thing, and that there might not be such a thing as dark energy? Could everything perhaps be answered by a modified theory of gravity?
Yeah, I mean, it is possible. It is. And there are modifications to gravity which do exactly this, right? You get into different questions. When you write down a theory, right, and you make these modifications to general relativity, people make arguments of naturalness. How natural or how expected is it to have something like this show up in the universe? Okay? And these are kind of deep questions, and people have some prejudices towards what is natural in a theory. So for example, if you've got to add in lots and lots of parameters and make sure these parameters have exactly certain values, this feels very fine-tuned and it feels very arbitrary, right? So when you're a theorist, you've got to make sure that you're not fine-tuning everything to be exact just so it ends up being exactly what you want. What you want is a very general theory which makes predictions, which we can then test against observations. So this notion of a natural theory and a simple theory really guides our intuition. General relativity, including this cosmological constant, the energy of the vacuum, is the simplest model we have, that lambda CDM. And anything else you add into that model is a complication, and then you have to justify why it's there. But sure, you can write down lots of theories of modified gravity with lots of different fields that interact and do crazy things. And they will also fit all those observations, but then you've got to explain why you've got 20 fields that you've added in and why they're interacting the way they are and why we don't see them all. You know, so it's the naturalness issue is kind of interesting. Yeah?
Could you explain again how, when you calculate the theoretical energy in the universe, how you use the existence state of matter?
Yeah, so you calculate the energy density given the expansion rate that you measure, for example, for the supernova. Okay, so you have Einstein's theory of general relativity, which is telling you a given expansion rate or a given motion of objects equals an amount of stuff in the universe.
No, I meant with the quantum, with the vacuum,
Oh, for the quantum
energy, the dark energy, the theoretical amount of dark energy that should be there.
Oh, I see. Yeah. So for each, so we have this quantum field theory, right, which is not easy to explain, the calculations of the mathematics behind that. But basically, in quantum mechanics, you associate probabilities with events, right? You can no longer say definitive things. It's just a probability for something to happen or not happen. Okay. And so you can add up the probability for these virtual particle pairs to pop into existence and disappear. Because the virtual particles that are popping into existence are associated with particles that we know about, we know the energy associated with these particles. Okay. We know the probability for them to happen in different places in the universe. Overall, this should give a non-zero energy density contribution to the universe. So it's literally summing up all those energies in a probabilistic way.
And it's related to the amount of mass matter that's there now.
So we think this is causing a dark energy field. Yes?
I think I heard that there was just recently the Milky Way became part of the super cluster of galaxies, and I thought I understood them to say that so there was an attractive force of the of gravity holding the supercluster together, and then there's the repulsive force, and I thought I saw that there was actually a delineation of the gravity force and the repulsive force. Is that a correct understanding?
So that's a good understanding of it. So this notion of on different scales, what is dominating how you move and your interactions is a very local idea. So within a galaxy, within this room, are we being affected by dark energy? Well, yes, but is it the dominant force? No. Our dominant force here is the gravitational attraction towards the center of our Earth, like downwards, and then also within our solar system, the gravitational force of our sun, and then our interaction with the other planets. Those are dominant forces, dominant gravitational interactions over the expansion or accelerated expansion rate. So within a galaxy, the dominant force there is the gravitational binding energy of all the stuff in the galaxy. And then when you talk about clusters of galaxies building up, or this local flow measurement, that is true. When you talk about the formation of superclusters, which are clusters of clusters, dark energy has actually prevented the buildup of these. Okay? So this is where you're starting to get the gravitational interaction between clusters of galaxies being disrupted. If there were no dark energy, we would get superclusters and superclusters building up. But dark energy has actually now stepped in on those scales and is starting to compete on those scales. Yeah.
When we talk about virtual particles popping into and out of existence, which particles are we referring to?
So you're associating these virtual particle pairs with all the particles that we know about in our standard model of particle physics. So there's a non-zero probability for these virtual particle pairs to pop into existence, and that's for each particle that we know about.
That includes quarks and photons and electrons.
And we've made measurements of these virtual particles, so we know that they exist. And so how is this possible? How can you just do this, right? You've no energy. How do you just suddenly create energy out of nothing? And that's because, again, simple intuition is wrong in quantum mechanics. In quantum mechanics, you're allowed to borrow this energy if you do it for a small enough time. So if you do that for a very, very small fraction of a second and repay that energy to make sure everything's zero, then that's okay. And this is called the uncertainty principle that is associated with Heisenberg, which is also a momentum space uncertainty.
Would that include dark matter particles?
So yeah, we don't know what the actual dark matter particle is, but if it's like in the standard model, it could have an antiparticle. It could be its own antiparticle. So we know, for example, the photon is its own antiparticle, right? So then, yes, it should have some virtual particle, non-zero probability for it to produce virtual particle pairs as well.
And that would affect the measurement of the background, of the vacuum energy.
Yeah, but it will still be a positive energy contribution, and it's not going to cause a cancellation to that 10 to the 74 grams per centimeter. Any more questions? Yeah?
Are there any advances in recent technology that helps you in this journey of finding out what this dark energy is?
Yeah.
Such as maybe measurements or maybe something that can help you in the simulations of the mathematical models that you're working on?
Yeah, so actually in all those areas, that's a really great question. In all those areas, we're benefiting from huge advances. So for the astronomical stuff, I'm not an observer, so I'll actually, if you're interested, we have Keith Bechtel. He'll be giving the guest lecture next week, and he'll talk about the dark energy survey and the actual details of the camera and everything there. But huge advances in terms of how we actually make measurements of the spectra of these galaxies and measure the distances from them. I know certain cool things that I've tuned into myself in talks over the years are that correcting for deflection of light through our atmosphere and things like this. We have adaptive optics, which are really cool, where you can actually deform the mirrors to correct for the effects of atmosphere, for light coming through our atmosphere, which is really cool. You can actually deform the mirrors in very short amount of time to correct for those things. On the simulation side, which is more what I work on, huge advances. So n-body simulations, where we do simulations of galaxies, right? We're talking about trillions of particles, and we're trying to follow the gravitational interaction of these over time. How do you build a galaxy? How do you build clusters of galaxies? And then how do you follow the physics within a galaxy, the gas and the dust and all those hydrodynamics, equations of pressure, temperature, and density? All of those things we need to follow in a supercomputer, right? You can't just do it on your laptop. I mean, you could, but it would be a pretty crappy simulation. So you need superclusters to do these things. And so there's very few places in the world where these are run. So for example, one place where they're being run is at Argonne National Laboratory, which is in a suburb of Chicago. And they have, I think it's currently the third largest supercomputer in the world. It's called Mira. And it's absolutely fantastic. It takes up like basically a whole floor of a building. And that is running a cosmological simulation at the moment that has been running for a few months, following the evolution of particles and how they build up into galaxies and clusters of galaxies. So you're not talking about one computer, you're talking about maybe 500,000 computers that are running these simulations. So the advances in technology in terms of the computer simulations has been through the hardware, through the technology. So combining things like parallel computing systems and GPUs. So these are graphical processing units, which were actually developed in the gaming industry. We take advantage of those for their speed and how they actually deal with the codes. And then there's been other advances on the coding side, actually writing more sophisticated codes and more efficient codes for how do we solve these equations of general relativity quickly and accurately. So there's been advances in all those areas, which has been amazing.
So do you feel like you're getting closer to an answer?
Oh no. I still think, I mean, the answer's not going to come from a computer, right? It's going to be from the observations. So, I don't know, I mean, it's hard to say because we're going after this value of W, right? And if we find that the W is close to a cosmological constant, right? It's pointing towards it being this energy of the vacuum. We still have this puzzle from theory of, well, why is our theory so large when our observational value is so small? So it's a combination of, I think the measurements, the observational measurements are exquisite and they're getting better and better and better. I think the problem now is on the theory side. We need more people working on the theory and trying to understand that.
Yeah, it's like, what are we seeing?
Yeah, exactly, exactly. So the observation guys are having a great time. They're making measurements of smaller and smaller error bars. The theory people are not really keeping up, so that's the problem. Yes?
Hawking, the British, tells in one book, in one essay in the book, that the Pope received the physicists, the astronomers at some meeting in Rome, and it was John Paul II, that he said, oh, he praised the astronomer for the great discoveries, but the Pope said you must not investigate the Big Bang because that's the limit between the normal and the non-normal.
Okay.
What is your comment?
Oh, yeah, no, I mean, so one of the things, I mean, I heard Mike Turner say once, he's professor here at the University of Chicago, is that cosmology, we don't do, the one question we don't do and that we don't answer is why. And I really agree with that.
Right?
Yeah. So, I mean, yeah, that's my response. Any other questions? Yeah.
I just have a comment. I was in a chemistry class a million years ago, and there was a student that was trying to ask the professor, why does this happen? And the professor said, we can tell you how it happens, but if you want to know why it happens, we all have to go over to the White Mule and discuss it over a few pictures of beer.
Well, I would agree with that. Yes.
I'll go to church. Stress energy. And secondly, when you have the borrowing of the energy in the quantum air production that has to be given back.
Yeah.
Why? How is there anything measurable resulting from that? If
So
you only have to
your question is very good, but I'm afraid that you really need to look at the mathematics. And if you're interested, I could point you towards many university books to look at. But these things are not easy to put into words. You really have to look at the mathematics. Yes. Yeah.
Just a quick question. So you talked about, like, one example would be like making the keep expanding, and the other one is like the big collapse. I don't know if this might be trying to apply some kind of classical mechanics, but is there a difference between like some part of the universe escapes out, the rest of it collapses in, and then you have a cyclical universe that keeps getting like smaller and smaller? Is that even
I mean, this would be a crazy theory. You could write down a stable equation for it, and that's cool. But the notion of getting expansion in different parts of the universe, different expansions in different parts of the universe, that's not so crazy. And then this idea of being one universe, which is next to many, that is a theory, right? That's called the landscape theory. And so that is, a lot of people like this idea that we're just one universe next to many universes, and that our questions of why are constants, why the value we measure for the speed of light, the value we measure for this dark energy density, why are they the values that they are? Their answers are, well, that's just the values they are in our universe, and there's infinity number of other universes where they take different values, and they're this value in this universe, and this gave rise to galaxies and stars and planets, and ultimately us. So this is called kind of an anthropic principle, and this landscape view is a view of lots of different universes where there's lots of things happening at different expansion rates in different universes, and things get pretty crazy. Sorry?
So we're just saying it because we had to.